what I thought I can do today, I want to talk a little bit about the book, and I thought I split it in like 3 parts. Just briefly introduce myself, then give a little bit of motivation of why we wrote this book and what's actually in the book and who is it for. And then in like the last bit and also the main bit, go into detail of one of the chapters, which is the last one, the last big chapter. And that's about like how you can actually pre-train your own transformer. So before we get there, just a quick note about me. I'm a machine learning engineer at Hugging Face. I work mainly on 2 things. On the one hand, I work on education. So I helped write the book. And also we have the Hugging Face course where you can learn more about the tools, the Hugging Face tools. I contributed there a little bit. And the second side that I'm working on is the open source team. In the open source team, we build all the open source libraries, for example, transformers, datasets, tokenizers, accelerate, all these libraries that some of them you might know about yet. We certainly go into more details in the book, especially about transformers, datasets, and tokenizers. And today I'm also going to talk about Accelerate, which is a new tool to train like at scale. My main projects at the moment evolve around code. So I worked on that model about code generation called CodeParrot. And that's also the topic of this last chapter that I'm gonna dive a little bit deeper into. But before we get into like the deep dive into pre-training a language model, I want to give like a brief overview of why we wrote the book and what's actually in the book. So about like 2.5 years ago, the landscape looked roughly like that. So when you wanted to learn about transformers, there were like great blog posts, for example, by Jay Alamar, which illustrated how transformers work very nicely, but on a fairly high level. Or on the other end of the spectrum, there were blog posts like the annotated transformer, which is very technical and requires already quite a lot of know-how to actually follow. And we thought, like, at the time, I was actually a data scientist at a company. And so the natural question I asked, like, I want to use transformers. I don't necessarily need to know like how attention works in very fine detail, but I need a little bit more than just a conceptual guide. So I need something in between. And that was like the main motivation to write the book, because we were looking around and there was no real like in-depth guide of how to apply transformers to like everyday business problems. So we decided to summarize the various ways how you can apply transformers into that book. So for those of you who haven't heard of transformers much yet, I doubt it if you work in machine learning, it's like that new architecture that's at the moment like taking over the whole machine learning community. It started with NLP, but now it's also branching out to computer vision and also to like other modalities and reinforcement learning. So who is this book for? So we target the book for people who are actually applying transformers to use cases. So it's perfect for data scientists or machine learning engineers who use transformers in their everyday work and would like to have like a in-depth guide of how to apply them. The way we structured the book is like we have about 10 chapters, and in almost all the chapters, we want to solve like a certain NLP task. There are like many NLP tasks. There's text classification, where you take a text and you just want to classify it. There is named entity recognition, where you want to extract named entities from text passages. There's question answering, where you ask questions about a certain passage and you expect the model to return the answer. There's summarization, where you have a long text and you try to condense it into a smaller piece of text that you can easily digest. And there's also language modeling, where you try to generate text passages based on maybe a prompt. And we cover all of these tasks. And at the same time, we try to pair them with like challenges that you face in everyday situations as a data scientist. So, for example, in one chapter, we do named entity recognition in a multilingual setting. So what if your texts are not only English? Sometimes when you read academic paper, it seems like the whole word is written in English language, but if you work in a country that's not natively speaking English, then you might get into trouble already. And we have like a chapter that shows a little bit like how you can bridge that gap, where you can actually use multilingual models to solve NLP tasks for many languages at once. In another chapter, we also look at like how you can deal with situations where you only have very few label data. So the most painful questions I always got when I worked as a data scientist was like, can you deal with like no label data or only a few label data? Because usually you don't have these nice academic data sets with thousands of labels. And we have a chapter where we go into a little bit more detail how you can do text classification if you have either no labels or just a handful of labels. In the early chapters, we also do a little bit of like introduction to the concept. So we go a little bit through the history of where transformers actually came from, like the previous architectures that motivated it. And then also a little bit more conceptual material on like what self-attention and transfer learning is and why it's so important for transformers. So that's like the bird's eye view of the book. And what I want to do today is I want to dive deep into the last chapter, which is pre-training a language model from scratch. By the way, I'm trying to, from time to time, just go through the chat a little bit to see if there's a question. And so if there's like a question I can answer right away, then you can post it. And if I miss it, I try to catch up at the end of the talk. So we want to pre-train a language model from scratch, but first we need like an interesting application. And if you've been like following machine learning, one like model that has been quite prominent in the news is Codex, or the application built on top of Codex called Copilot. And what that model does is it predicts, language models generally just predict the next token, and Copilot or Codex predicts the next token or the next word in code. And that can be very useful because with such a model, you can essentially autocomplete coding. And you can see here an example where you have like a comment of what you want to do. You want to determine the sentiment of a text using a web service, and there you write a function header, which is called like a function called isPositive, and then Copilot autocompletes that function for you, which is quite handy, especially if you have like a lot of boilerplate code that you usually need to write. And so the question is, how can we build such a model ourselves? Let me see, there is already a question. Is NLU also under the umbrella of Hugging Face? So if I understand correctly, NLU, you mean natural language understanding? And yes, like the Transformers library was mainly built in the first place for NLP, so natural language processing. And NLU is like a subtask of NLP. So NLU is usually the tasks around classification or named entity recognition or question answering. Usually those are referred to as natural language understanding. And yeah, there are lots of tools to work with those for those problems. Cool. So back to language models. We want to, in that chapter, we want to build a model that can generate code for us, hopefully meaningful code. So if you look at like what the landscape of these code models looks like, I had to update that actually this morning because the field is progressing quite rapidly. These are all models that were trained for code, some of them for code generation. And you can see the ones in blue are ones that were publicly released, and the ones in orange, those are private ones that were never publicly released. And you can see a few models called GPT-Neo, GPT-J, and GPT-Neo-X. Those are not dedicated code models. They are more general open source versions of OpenAI's GPT models, but they were trained on a subset of code. So they're actually reasonably good at coding, but they're not dedicated code models. On the other hand, you see models like Polycoder or Codex, and Google's model they released in 21 by Austin et al., or AlphaCode that was recently released by DeepMind. And these are all dedicated code models. So these models were trained on code, usually from GitHub, and they're pretty good at these tasks of generating code. You can also see CodeParrot, and that's actually the model we train in the book. And at the time, it was one of the largest pre-trained code models. And we released it, I think, last November or December. And since then, Polycoder came out, Encoder and CodeGen just came out like a few weeks ago. And also AlphaCode wasn't released at the time. So you can see that field is progressing quite rapidly. So let me see, there are a few questions. So in the book, if you mean like there's a question, do you use a mix of JavaScript and Python in the book or only JavaScript? So in the book, we only use Python. The whole book is written in Python, primarily in PyTorch, but we also have examples of how you can translate the code in the book in the book to TensorFlow. All these models are trained to do the same thing, the same task. Yeah, so all these models are essentially pre-trained to predict the next token in a sequence of tokens. So they get as input a little bit of code, and then they need to predict the token that follows or the code that follows. And they pretty much all use like almost the identical pre-training objective. Where are the public models available? Couldn't find them on the hub. So CodeParrot should be on the hub already. Polycoder, we're currently adding to the hub, and the encoder should also be on the hub. We just added that one last week, and CodeGen is at the moment on GitHub, but might be also added to Hugging Face at some point. No, so one person asks, like, aren't transformers pre-trained always? And I mean, generally throughout the whole book, we usually use pre-trained transformers, but there are scenarios where you want to pre-train your own transformer. And that's especially true if the target domain, so where you want to apply the transformer, is very different from the pre-training domain. So usually transformers are pre-trained, for example, on natural language text, so a web scrape. And if you want to apply such a model then to, I don't know, maybe amino acid sequences, then the model doesn't work quite well because it has never seen data like that. And in these cases, it can make sense to pre-train a transformer from scratch. Cool. So I'm gonna move ahead a little bit and then answer a few more questions in a minute. So before we can train our own model, the first thing we need is a data set to pre-train a transform model. And the natural thing to do here is go to GitHub. So if you want to build a model for code, GitHub is like a very rich resource of code data. There's a public data set on Google's BigQuery with GitHub data. I think it has about 3 million repositories. And what we did because we wanted to simplify the training a little bit, is instead of training on all sorts of code, we focused on Python files only. And if you select all the files that are in BigQuery, you get about 160 gigabytes of data. Once you deduplicate it, you have about 50 gigabytes of data left. And you can already see that that's quite different to the fine-tuning domain. Usually when you just fine-tune a transform model or any model where you can use transfer learning, usually they don't require a lot of data. Usually with a few thousand labeled examples, you can already get pretty good results. But if you want to pre-train a model, you actually need lots of data. So we have about 50 gigabytes of data. That might already be like on the lower bound of what's useful. So ideally, we would like to train on even more data. Recently, we released a similar data set with more languages, where we have about 1 terabyte of data. So we collected a data set like that. So now we have like 50 gigabyte data set with code. And that might already be challenging depending on your laptop or your machine you're working on. So if you want to load a data set with 50 gigabytes of text data into memory, so if you, I don't know, use pandas and you do just load a data frame with all that data, usually it even requires like a multiple of like the raw size. So maybe instead of 50 gigabytes, you might require like 100 or 150 gigabytes of RAM, which is quite a lot. But if you use the datasets library, which is part of the Hugging Face ecosystem, it comes with like a few quite nice features that help you deal with like very large datasets without running out of RAM or disk. And the first is memory mapping. So if you load any dataset with the datasets library, and you can pretty much load any kind of data right now. So it can be text, but it could also be images, for example, or audio data. The data is actually never fully loaded into RAM, but it's memory mapped. So the disk becomes like an extension of your RAM. And that makes dealing with like very large data set much easier, because then loading a 50 gigabyte data set might just require like a few gigabytes of RAM, which is quite nice. If you have like a very, very large data set, another issue might be that you don't even have enough disk to store the data set locally. That's where the data streaming feature comes in handy. You can use dataset streaming to just load a data set continuously. So you just load the samples you currently look at. What that means under the hood is that you have a generator that generates data for you. And as you loop through the data, it's progressively loaded from the hub. And in the pre-training chapter, we use both these features to pre-train the language model. And so you don't need any disk and you don't need much RAM, and you can train a language model on like a few terabytes big data set. Let me see if there are any questions that I can see that I can answer. So one question is about if the models I showed share the same input and how that impacts like the number of parameters. And that's indeed true. One thing that's different between those models is usually they have like, each one has a dedicated tokenizer. The tokenizer is responsible for splitting a string, so a text, into small pieces that are then, usually you can think of them as kind of words, usually a little bit smaller than words even, so subwords. And usually each of these models has an individual tokenizer, and how you design that tokenizer is very different. For example, AlphaCode, which is a very large model, they used a very small tokenizer with only like 8,000 tokens. Codex uses a tokenizer which has 50,000 tokens. So there are like differences and there are some trade-offs. So if you have a large tokenizer, that might require more parameters and more memory. At the same time, you're more efficient at splitting your text as if you only have like a very small tokenizer. There's another question about how time consuming it is to train with such huge data. I'm coming to that in a minute. How to use or add my own additional vocabulary dictionary, place tokens, or add new ones. So the question is, if a pre-trained model has a fixed vocabulary, can you add new tokens? And yes, you can. Usually in the transformers library, there is a function called, you can add tokens to the vocabulary, and then you can also resize the model so it can deal with the additional tokens. Obviously, you then also need to train with those new tokens because the model has never seen them before, so it doesn't know how to deal with them out of the box. So another question is like how many steps usually to train until you reach convergence. I'm also coming to that in a second. To the second question, which checkpoint do you start with? That's also different. So OpenAI with the Codex model, they just use a GPT checkpoint, so just a general language model, and they just train it much longer on code. Other models such as AlphaCode and also CodeParrot, they start from scratch. So you initialize a fresh model and then you pre-train from there. And the last questions I can answer right now is, are there GPUs good enough or is TPU a must? So in general, like GPUs are also good enough. It usually depends a little bit where your compute comes from. Sometimes people get some resources on for example, the research cloud from Google. So they get access to TPUs, so they train on TPUs. We trained on GPUs to keep it a little bit more general, and that also works fine. But for pre-training, it makes sense to go for like modern graphics card as it's much more efficient. Cool. So I'm gonna continue and answer a few more questions in a minute. So we have a data set now. So the next thing is we need to figure out how we can train such a language model. So here's an example of what a code snippet might look like from our data set. You have a function, you have the function header, we want to add two numbers. You have a doc string that explains what that function should do. And we have the body. And in that case, the body is simply returning the sum of A and B. So there are now various different ways of how we can approach this, this data set. Two of the most common ways to do it is mask language modeling and causal language modeling. So in mask language modeling, you take the input and you replace some of the tokens by either a random token or by a mask. So you can see in that case, we replaced the definition with a class and we masked the two in the doc string, and we added a mistake in the return statement. And then the goal of the model or its objective is to predict the original input. Usually for these type of tasks, you use an encoder, and very prominent examples of that family or that kind of model is, for example, BERT. BERT is trained like that, and these models are also usually very good at these natural language understanding tasks. So where you have an input and you want to, for example, classify it or do an identity recognition or question answering for these type of tasks, these encoder models are really good. There is a second family of models, the causal language models. And instead of randomly masking or replacing tokens in the middle of the text, it replaces it at the end. So a causal language model always has to predict the next token based on the previous ones. And you can see here, for example, the next token would be what's actually returned. And the goal of the model is to predict what to return. And these models are usually done with a decoder architecture. GPT is a famous example of that, and the whole GPT family, so GPT-1, GPT-2, and GPT-3, they're all decoder-only models, and those are usually very good at NLG, so not NLU with like natural language understanding, but NLG as in natural language generation. So they're very good at generating text. There are famous examples where they generate text of unicorns, for example. For completeness, there's a third option. These are the sequence-to-sequence models. And what they do is they split the input and output texts into separate pieces. So for example, the input could be the docstring, so just the description of what the function should do. And the output could be the actual function body and header without the docstring. Another example that you might know or might have heard of or played with is translation. That's usually also framed as a sequence-to-sequence model where you have as an input a sequence in one language and as an output in another language. Or another example is summarization, where the input would be a long text and the label would be the summary of the text. So these are the three options we have. And if you look at the models I showed at the beginning, the majority of them uses a decoder-only architecture. So Codex, Polycoder, GPT, Neo, and GPT-J, they all use a decoder-only architecture. The only exception is AlphaCode, which uses an encoder-decoder architecture. But that's also a special case. They focus very heavily on a certain type of problem structure. So let's see if there are a few questions. Does the book cover guidance on neural network architecture for NLP as well? So we mainly cover transformers as the main architecture. We cover like some architecture choices within transformers. So similar to what I just went over with the encoder or decoder or encoder-decoder architectures. But if you want to have a more general overview, we have some references at the beginning of the book where you can read other books that go into more detail in that. Another question is how much data is needed so that fine-tuning can be enough? So if you just want to fine-tune a transformer for use case, it depends a lot on how far your data distribution is away from the pre-training distribution. So if you want to do something that's very similar to what the models was already trained on, sometimes a few labels are enough, or maybe a few hundred. If it's something more complicated, maybe you need a few thousand labels or tens of thousands of labels. There's no like general rule to do that or to estimate that. The only real thing is like just trying it out. Another question is, do you recommend using a pre-trained model for multi-class classification of spam? Yeah, definitely. So if you want to classify something like spam, that's very natural text, then definitely try out pre-trained models. There's models like BERT or even better, Roberta or DBERTA, which are like newer variants that are more performant than the original BERT. And if you, for example, have something that's multilingual, so many languages, you can check out XLMR. That's a really good model to do multilingual stuff. Unfortunately, I can't give an example of a model on ImageNet, but we're currently adding a lot of examples on that. And I think if you go to the Hugging Face Transformers repository, you're going to see that there are now many more examples with vision. So maybe you find what you're looking for. Can transformer do both encoding and decoding? So in general, the transformer is like the umbrella term for all the architectures that I just showed. So the original transformer was an encoder-decoder, so like AlphaCode here. But usually people also call like the decoder-only models transformers. But in general, yeah, so depending on the architecture you choose, you can do encoding or decoding or both. In the decoder, what is the data type? So the decoder takes as input a text and as an output also predicts text. So it gets an input text and needs to predict the next token. And then the final question to answer right now is like, where is attention? So attention is both in the encoder and decoder. And I'm not planning on going into detail here about what attention does exactly, but essentially it helps the encoder and the decoder look at the long sequences and shift the attention to certain tokens and doing kind of like a weighted average between all the inputs it gets, because the transformer gets all the tokens at the same time and then needs to kind of prioritize which tokens to mostly look at. And the attention is hidden in what's here, the encoder and the decoder. And in the book, we have like a blown up version of that, or an exploded version of that graphic, where you can see into what the encoder and the decoder actually does. So I'm going to continue, not to run out of time, and then hopefully answer a few more questions at the end. So what we decided to do is go with the mainstream, also do a decoder only architecture. And so the next thing we need to do, we have the data set and we have the architecture. Now we need to make sure that the data goes well into the model. And what you can see here is a few samples of text, how they would look like after you tokenize them with the tokenizer. So as I said previously, the tokenizer does split the text into smaller chunks. And do you have like code samples that are very long and some code samples are very short, and they will have like different numbers of tokens. But what the transformer architecture has is like it has a fixed window length or context length. And that context length essentially says like what's the longest sequence the model can look at the same time. And during pre-training, you essentially always want to max out that context length. So you want to feed in sequences that are as long as possible for the model to train. But if you look at the three samples I show here above, like one is exactly the right length, one is too short, and one is too long. And the simplest thing to do is maybe we could just cut off the ones that are too long. Maybe we could pad the ones that are too short. But that would mean that the ones that we pad, the model looks at like just padding for a long time, which is inefficient. And if we cut it off the samples that are too long, on the one hand, we're wasteful with our data. And we also might lose systematically information that's maybe more at the end of files. So we don't want to do that. And an alternative thing to do is just concatenate all samples and join them together with what's called an end of sequence token. And so the model knows when it sees the end of sequence tokens that the previous sequence has ended, and then whatever comes next is independent of that. So that's what we did in the pre-training. We have like a data loader that does that on the fly. And if you want to see the code, you can go look at the book, or I also share the repository where you can find all the code online. So now we're almost ready to train. We have the data set, we have the pre-processing, we have the model. But because we're doing pre-training, we actually need a lot of resources. So you can't pre-train a large language model on a single GPU. I mean, you can, but it will take like very long time. Usually what you want to do is you want to train it on a larger infrastructure. And we went for like a multi-GPU machine, so a machine that has 16 GPUs, and we want to train it there. Now, if you look at on the left-hand side, what you see in black and green and in black and red is essentially pure PyTorch code. So if you have a PyTorch model, that's what you would do. You have like your model, you put it on a device, which would be the GPU, for example, and then you would write your training loop. But that works well for one GPU. But if you want to go to multiple GPUs or multiple nodes, so if you don't have only one machine, but several machines with many GPUs or TPUs, you need to adapt your code. And that's where another library called Accelerate comes in handy. And what you can see here is essentially that you replace the red parts with the green parts, and suddenly your code can run on a CPU, it can run on a GPU, and it can run on a TPU. So that's very minor changes that have a very big effect. It gives you a lot of flexibility to experiment with your models first, maybe on your laptop, and then once you're ready, you can just go on a big machine or on a cluster without actually needing to change anything. So that's just a side note on a cool library that you can use when you need to do like distributed training. So let me see if there are any questions. How do you adapt your vocabulary to and tokenization technique? I don't have that much time to go into detail here, but essentially, usually you train the tokenizer on the data set you want to use it on. So we trained a tokenizer on code, and that kind of guarantees that it's quite efficient at tokenizing code. So you mainly need to choose like how big your vocabulary is. And we did that by looking at Python keywords. So we looked at how large do we need to make the vocabulary until the tokenizer tokenizes all the keywords that are in Python efficiently. And once we had that, we thought that's efficient enough. So I'm going to talk about like how long it takes to train and the infrastructure in a minute. So we trained what kind of corpus is used for pre-training? We used GitHub corpus. So we pre-trained on code and Python code that we got through BigQuery. And lastly, is the accelerated library also available for Cuban vision training? Yeah. So the accelerated library is actually completely agnostic to the task. So what you see here on the left, I mean, that has nothing to do with natural language processing or nothing specific with natural language processing. You can see you have some PyTorch data loader, you have an optimizer, and you have a model. And what they do, if they do reinforcement learning or if they do computer vision, doesn't matter at all. So you can use it for any infrastructure that any task that you want to do. So I'm gonna continue to hopefully finish soon, so we can answer a few more questions towards the end. So that's all. That's just a small sketch that shows you how to actually train on multiple GPUs. To speed things a little bit up, the gist of it is you have like a central data loader that gets all the data, and then a batch. It distributes batches to each GPU, and each GPU does the forward backward pass, calculates the gradients, which are averaged, and then the models are updated on each GPU. So you make sure that you have the same model on every GPU. So we did that. We trained that model on A100 GPUs on GCP, on Google Cloud, on 16 of them. That's the largest machine you can get, which is a single machine. And for the small model, which has about 100 million parameters, it took about a day or two. For the large model, it takes about 10 days to run that. If you look at the pricing of 16 GPUs, that's quite expensive. So you should only really do pre-training when you have data that's very different from the normal pre-trained models. So we don't suggest pre-train all your models for all your use cases from now on. Just do it for dedicated use cases. Then just finally, something we don't touch on in the book so much is evaluation, how you can do that. And a common benchmark is human eval. What you get is essentially such functions, and you have like a header, a docstring, and a body. And as an input, the model gets everything except the body. So it gets the header or the signature and the doc string, and then it needs to predict the rest of the function. In one handy thing, when you work with code, you can actually evaluate how good the generation is with unit tests. So if you have a function, you can define a set of tests that that function should pass, and then you get whether the function does what it should do. One thing that's a little bit bad or doesn't work so well with that approach is that on the one hand, you generate functions with a model, and usually you sample the generation. So you can have some variations in it. And what that also means is that for the same problem, some of the generations of the model might pass and some might not. And if you only do one test, then you have something that's very noisy. So might just depend on the random seed that you chose when you did the generation, something like that. So OpenAI came up with a new metric that's called pass at k metric. And what you do is you generate k solutions, and then you see if any of these solutions pass. And for any given task, it is considered solved if any of the k generations passes. So pass at 10 means the model generates a good solution at least once in 10 generations. And here you can see a few results of different models. So you see the polycoder model, you see CodeParrot that we trained in the book. In red, you see a slightly updated version where we trained the model a tiny bit longer than the original one. And you can see that the performance improved of that model. You can also see that we trained for a fairly short amount of time. We trained for a week, but that we only trained for like 26 billion tokens. So the model only has seen 26 billion tokens during training. Whereas if you look at other models, they train for much longer. So Codex, which is a fine-tuned version of GPT, they even train for 100 billion tokens. And in AlphaCode, they train for even longer. So with that minimal setup, you actually get already like quite nice results for a smaller compute budget. Oops. So that concludes the things I want to talk about. I know I went pretty quickly over the evaluation, but you can read up on that, I think, or can ask more questions about it. I thought it might be more interesting to answer your specific questions now. Here are just a few resources that might be interesting. All the code to pre-train, evaluate the model are in the Transformers repository. The model itself you can find as well on the Hugging Face Hub, as well as the datasets. The CodeParrot Clean Train dataset is the one we use for CodeParrot to train it. The GitHub code dataset is a newer dataset. That's the large one with 1 terabyte of code. So it has much more code than only Python. So if you want to go ahead and build your Docker file generation model, you can look at GitHub code. It should have like plenty of Docker files too. And lastly, if you want to play around with these models, we have 2 spaces. Spaces are like demo platform where you can play with CodeParrot to generate code, or also to use the model to highlight code and to find bugs. So I think with that, I think if you want, you can raise your hand now and we can unmute you so you can ask questions in person, or I can go through the questions in the chat and see if there are some left that are unanswered.
Great. Just a quick reminder, if you have questions, you can post in the chat, or if you prefer to speak to ask questions, you can raise your hand. I can unmute you. You can have a discussions.
Exactly. So what is the advantage of Accelerate versus PyTorch Line A? So I'm not a huge Accelerate expert, but the way I see it is that Accelerate is more like a simpler version or a more bare bones version of PyTorch Lightning. It does a lot of things under the hood and requires like very little configuration at that. And PyTorch comes with many more features like kind of a trainer and things like that, which Accelerate doesn't have. On the other hand, if you're in the transformer ecosystem, you also have a trainer. So a trainer class. So if you want to do distributed training and you have like a fairly straightforward training loop, then you can just use the trainer and you don't need to write everything in Accelerate. How would you recommend injecting numeric features alongside word tokens? For example, if for each token you have a time difference, a sentiment score, etc. That's a good question. So if you have like a lot of data, you could try to pre-train like a custom architecture, but that would require like significant compute. Depending on the task that you have, you could try to integrate that data into the head of the model. So during pre-training, you train like a model body in a sense and a head that does like the next word prediction, for example. And if you then apply to something like sentiment classification, you just replace the head with a classification head. And if you have like a specific task, you can customize that. So all the transformer models, they're just PyTorch code. So you can plug your own PyTorch head on top of the model. And I think people have already done that. So if you go into the Hugging Face forum and look for that, I think there are people who did like custom heads. How would you recommend pre-training models for word embeddings with your own content? For instance, want to use embeddings first to find similar terms near each other. There's a very cool library called Sentence Transformers, and that library is also using transformers under the hood, but it's specifically designed for that type of problem. So you can do a lot of tasks related to similarity. So if you want to do retrieval, for example, it's very well suited for that kind of thing. So I would recommend checking out Sentence Transformers. I can write it in the chat maybe. Let's see. So how can we compare two transformers used in a chatbot? I'm creating a French chatbot based on Rasa using Hugging Face. So I felt it's natural to use Camembert instead of Bird, but I didn't see the difference with the trained bot. So in general, I would try to set up like an evaluation benchmark for your models. So for example, if you do translation, what you do is you have like a test set and you calculate scores like bleu or rouge on that. And I'm not so familiar with chatbots, but I would imagine that there are similar data sets and you could try to play around with different kinds of models to see which ones work well on that task. I'm interested in text classification. Can CodeParrot be used for the same, or is it a pure natural language understanding oriented architecture? So CodeParrot is a natural language generation oriented architecture, but you can use these architectures as well for classification. But usually encoder only architectures like BERT work better for these tasks. But you could try give it a spin. In the transformers ecosystem, it doesn't really matter whether you have a model like CodeParrot or a encoder only model. The interface is the same, so you can quickly play around with different architectures and see which ones work better. Let me see. how can we check if our data set for fine-tuning differs from pre-trained data set distribution? I mean, the thing that I meant is when I said you should only do pre-training when like the data set distribution is very different, it's like it's so different, it's obvious. So in case of like CodeParrot, like if you look at what kind of data the normal models are trained on, it's natural text. It's like stuff like Wikipedia and so on. And if you look at code, it's very obvious that it's very different. Or if you go look at amino acids, you know, you find very quickly that it's very different. Another thing that you might want to take into account, whether you want to pre-train or just fine-tune, is the tokenizer. So if you create a dedicated model, you create a dedicated tokenizer, which is usually more efficient, and you can compare how much more efficient it is at tokenizing. So if you have what we did, for example, with CodeParrot, we looked at the normal GPT-2 tokenizer, and we looked at the CodeParrot tokenizer. And the CodeParrot tokenizer uses twice as few tokens to tokenize the same text as the GPT-2 tokenizer. Because in code, you have a lot of tabs and new lines and things like that. And when you train a model on that, then, or tokenizer on that, then it gets very efficient at that. Can a generative model be used to retrieve representation? Yes, it can. So in any model, you have hidden states, and you can use these hidden states as kind of a representation of the code. As I'm not a retrieval expert and an embedding expert, but to the people I spoke to, usually encoder-only models like BERT perform better at creating these embeddings. But we also used the CodeParrot embeddings recently to just visualize the data set a bit, and you can see that it learns useful representations. I guess we're over time already. Should we continue answering a few more questions? What do you reckon?
Yes, please. We can finish the rest of the questions.
Cool. For just fine-tuning, how much compute does one typically need? Are GPUs still required? So even if you fine-tune, because these models are very large, it's very computationally expensive to fine-tune them. So if you do it on a CPU, I mean, it's doable, but you need like a lot of CPUs and you need a lot of time to do it. Usually just fine-tuning, if you have even a simple GPU, takes maybe a few minutes or maybe a few hours at max. And if you don't have a GPU, there are many like free versions or free platforms where you can use GPUs for free. So for example, there's Google Colab. If you want to use GPUs, you can use Colab. They also offer TPUs, as far as I know. And actually, that reminds me, I can show you quickly the website of the book. Oops. So if you go to the book's repository, you can see each chapter is essentially a Jupyter notebook, and you can open it in any of these platforms. So you can open it on Colab, Kaggle, Gradient, and Studio Lab, and they're all for free and all give you GPUs. So if you want to do something with data that's maybe not so sensitive, you can do it here for free. I think the only requirements is that some of the platforms require you to log in or to create an account. But besides that, all of them offer free GPUs, which is quite nice. Let's see. I mean, if I missed any questions, you could also just copy paste them to the end. So. So for vision, I think if you go to transformers, Hugging Face transformers, there's examples. And here you can find example. So the question was if I can give you an example of a vision model trained on ImageNet that one could use for image tasks. And you can see here, there's both a notebook, I believe, or a file, it's a file, a script to run the pre-training for images. And there's also an example script of how to do image classification with such a model. So a vision transform model is, for example, VIT, vision transformers. And there are examples here that you can look at. And there are examples for many more tasks. So if you need anything, that's a good place to look at.